All right, class, let's do lesson 4. In this lesson, we're going to learn about scattergrams or scatter plots, whatever you want to call them. There's always a million different things that we can call everything in statistics because it's weird like that. And then we're going to learn about linear correlation. Okay, so let's just jump right in. All right, so we're going to learn how to make a scatter diagram, scatter plot, scattergram. Like I said, there's a million different ways you can call like each thing in statistics. So they all mean the same thing. Then we're going to look at correlation coefficient R. We're going to figure out what that is. And then we're going to figure out what is causation. And also we're going to bring up lurking variables again. Okay, so scattergrams. In scattergrams, you are going to be graphing X and Y pairs. What does that mean? Well, first of all, let's look at the axes. So we're going to have two different axes. We're going to have our x-axis and our y-axis, okay? And these two pairs are usually graphed against each other, I guess is how you can think about it. They're being graphed against each other. This is usually going to be in any kind of situation where you think that you want to see if x, whatever variable you have for x, is going to cause something to happen to y, okay, to your y variable. And we'll look at how that actually works in a moment. And then we have the y-axis, which is this vertical one. Okay, these ones. And the y-axis is going to be your dependent variable or your response variable. So essentially, x is like the independent variable that causes a reaction, okay? And x, the y-axis is the dependent variable. So dependent variable, this is the response to the x-axis or the x variable. Okay, so x causes y, if you will. All right, but anyway, how to remember exactly like which axis or which axis goes on what? Like, is it vertical? Is it horizontal? What the heck? I don't know. Always know that, like, here's a good way to find out. You can take the letter y right here, a capital letter Y. And if you were to like take its tail right here and just yank it and drag it all the way down, you can see that it creates a vertical line. Okay, so that is kind of a good way to remember that the y-axis is the vertical axis. Okay, and then of course then you would just assume by process of elimination the x-axis would be the horizontal one. Okay. So there's also a trick to memorizing, the fact that the x-axis is the independent explanatory variable and the y-axis is the dependent response variable. Okay, so you know how you learn the ABCs when you're a kid, and if you go through all the ABCs, you know the last part where it goes W, X, Y, Z. So the X comes before the Y in that, okay? So if you go through that order, X comes before Y, which means X causes Y to happen. Okay, so X is independent, X stands alone, X is its own person, right? But it causes Y to happen. So since X comes first, it causes Y. And that makes Y the dependent variable. It's dependent on X. Okay, so that's just a way to think about it. If you need that explanation, there it is. Okay, so let's go ahead and see how in the world you can, create one of these scattergrams. Okay, here, let me go ahead and let you guys know that this is the x-axis down here. Okay, so anyway, Okay, so let's say what we're studying or what we're trying to figure out is if the number of diagnoses that a patient has is correlated with the number of medications that he or she is taking. Okay, so in the x-axis we have the number of diagnoses that the patient has, and in the y-axis we have the number of medications that they are taking. Okay, so we want to see if X causes Y to happen. All right, so if the number of diagnoses that the patient has is causing to have a lot, or a little bit of, medication. Okay, so we want to see if there's a correlation there. So what you're going to do is go ahead and let's plot the first one. Okay, so how we're going to do this is you want to take your x-axis first, okay, take the first number, and we're going to go ahead and plot that, or we're going to find that, okay, on the x-axis, which is over here. So we go to 1, all right, and then the number, so we go to 1, and the number of medications that this corresponds to is 3. So on the y-axis, we find 3, and go ahead and plot that first one right there. Okay, it's that easy. I'm sure some of you guys probably already did this in algebra class long time ago, but maybe you need this refresher. Okay, so next one. I went ahead and I went ahead and plotted all the other dots, but let's go ahead and go through them anyway. All right, so for the next one we have 3, so we go to 3, and then our y-axis we have a 5, so we go to the 5, and then we go ahead and plot it right there where they meet. Okay, then for the next one we have our x is 4 and our y is 4, so we find 4, right, and then we find the other 4 on the y-axis, and we go ahead and plot it right there. Okay, and so for the last one we have the x is a 7, the y is a 6. So we're going to find the 7 on the x-axis right here, and it's up there, and then we find the 6 on the y-axis, and haha, there it is. Go ahead and plot it right there. I mean, you don't have to draw the lines, I just did that to show you guys what you're going to be looking for on both axes. But hey, if it helps you to draw the lines, draw the lines. Okay, so that's what it is. That's just very simply how you would create your little scattergram. Okay, now, so what is linear correlation? Well, remember in algebra class, I hope you guys remember, sometimes they would give us these little tables, right, where they would say, go ahead and plot x and y, and then we would do that, like after we solve our equation, and then we would find the points for the x and y's, and then we would plot them, and then usually in those math problems, we used to always get like perfect straight lines, huh? But the thing is, in real life, we usually don't get perfect straight lines. See, a linear correlation means that when you make a scatter plot of your x and y pairs, it should look like a line. This would be a perfect linear correlation. Real life does not always look like that, okay, but it can come close to it, okay? You can, many times when we see like, dots, we can all, the scatter plot, the scatter points all over in our graph, we can kind of see that these points are going in a certain direction. So we can actually draw a line that comes close to what our points are doing, what our points are trying to show us. Sometimes it doesn't always happen this way, but we can come close. So let me show you an example. So this would be called a positive correlation. Okay, because look, we have our dots, and of course they're not in a perfect line when you connect them, but they do kind of make sort of a line, right? So we can literally just draw a line in the middle of all of our scatter plots, and that would be our linear correlation. And we would say that this has positive correlation because as you move in the left to right direction, okay, it's going up. So we would say that that is positive. Now in this situation, how we would read this is we would go, well, these are the number of medications, these are the number of diagnoses. So remember in our last one, it was like, do the number of diagnoses correlate to the number of medications that they take? Well, it looks like in this graph, it's telling us that the more the patient, more diagnoses that the patient has, the more medications that they take. So there is a positive correlation there. Okay, so that's how you would interpret that graph. Now, now it's not always going to be a positive correlation. Okay, so let's look at this next one. We're doing patient number of patient complaints. So, you know, the amount of times that patients complained about maybe their the service that they're getting from the hospital. And then over here, we want to see if it correlates with the number of nurses that are staffed on that particular shift. Okay, so we go ahead and plot our points, and then we see that it looks like it has kind of a downward, you know, line. Looks like that's what the graph is showing us, right? So that's where we would draw our line. And when it goes downward as you're going left to right, when it does that, that would be called a negative correlation. Now, it doesn't mean that something is bad, something bad is happening. It, like a positive correlation or a negative correlation, that doesn't really mean that, oh no, something terrible is happening, we have to do something. It's just really telling you what the numbers, what is actually just happening in that situation. Okay, so we don't need to panic because sometimes this can mean a good thing, sometimes, okay, yeah, it can mean something bad. But in this situation, it actually means something good. So let's interpret this graph for a second. Okay, so it looks like what it's telling us is that, you know, down here where you have just maybe like one, or, you know, maybe if we have a lot of complaints, number of patient complaints, that corresponds to having only like one nurse on duty. Okay, only one nurse, only one staff nurse on that shift. That's probably why there were a lot of complaints at that point. Okay, because there was only one nurse working. That one nurse couldn't handle everything. But if you look at, there's only one complaint here, and that corresponds to having 7 nurses that were staffed. Okay, so it seems like this graph is telling us that the more nurses we have staffed during a shift, the less complaints we're going to have. And the less nurses we have staffed during the shift, the more complaints we're going to have. Okay, so that's just what this graph tells us. So that doesn't mean a bad thing. Yes, it's a negative correlation because the line is going downward when you move from left to right. Okay, so what if it's kind of a mess like this? What if it's just doing something and you can't really see if it's going up or down? It's not, you know, doing anything obvious. Well, in this situation, your linear line can just be, it can just be a straight line. There's probably no correlation here because if you look at it, the plots are everywhere. So you don't really see any kind of correlation. It's not like as you have more visitors, okay, it's not like the more visitors you have, the more that correlates to the more days you spend in the hospital. Because as you can see over here, when you have only, patients only have like one visitor and they're spending, you know, an entire week in the hospital. Okay, and then you see some patients who had like 4 visitors and they might only be spending 3 days in the hospital. Some patients who have 7 visitors, same thing, 3 days in the hospital. So this graph has no correlation, and that's okay to not have a correlation. It's just we do these graphs so it can allow us to see whether or not there is a correlation. You know, if the X is actually causing the Y to happen. In this case, it does not look like the X is causing the Y to happen, okay? And the previous ones, if you know, with positive and negative correlation, you do see a pattern where it looks like the Y is causing the X is causing the Y to happen, you know? Okay, and then we have this last one. Sometimes it can be goofy, you know, and you don't, here in this situation, there's obviously no correlation, and it seems like there's not really any line that you can draw either. So you can't draw a line. Your line would be goofy. You know, I don't even know how a line would be drawn in this case. But anyway, this graph does not really make sense. It's clearly there's no correlation, and Y or X is not causing Y to do anything. It has nothing to do with Y. Okay? Okay, so correlation actually has two different attributes. So we already kind of looked at the direction and what that sort of means. Okay, so that's just the direction of where your correlation is going, or you know, how your two data points or your two different variables are related. Okay, and remember we looked at positive correlation, which is where it does this thingy, and negative correlation, which is when it does this. And then no correlation, which is when you can draw like just a straight horizontal line or no line at all. Okay, but that's not the only attribute you can look at when you are doing scatter plots. Okay, so we can also look at the strength. Okay, so the strength of your scatter plots refers to how close the line is to your dots. Okay, so if all of your dots fall really close, super close to the line, then we would say that it is really the strength, it's strong, okay? And if they all fall kind of far away from the line, or maybe not necessarily far away, but kind of close, but not too close, we would just say that's moderate, okay? But if they're like really far away from the line, okay, they aren't very close to the line at all, it's still a clear direction that it's going up or it's going down or something like that, but they're just not falling close to the line at all. We would say that that is weak, okay? Okay, so here's an example. Look at the points or the scatter plot in the left-hand side. Okay, as you can see, all these dots, our direction is negative. Okay, so we have a negative correlation happening here because it's going down as we move left to right. And then look at where the dots are in comparison to the line. They're actually pretty close, aren't they? They're somewhat close to the line. They're pretty good. So for this one, we would call it strong negative. You know, if it's about this close to your line, it's pretty strong. Okay. Now look at this one. Okay. This one is definitely positive because as you move, from the left direction to the right direction, it is going up. Okay, so that would be positive. That's our direction, right? And if you look at the plots, they're not too far away, but they're not very close either. Okay, so this is definitely a moderate kind of a strength. And then you can look at this example. Okay, so it's still a positive correlation. It still has it's in a direction where it's going up. But if you look at the plots, they're all kind of like doing their own thing. Everyone's far away from the line. And whoa, what is this? That looks like an outlier. Okay, so this type of a correlation is going to be weak. Okay, it's a weak positive correlation. Okay, so outliers in correlation, as we saw in the previous graph, we did have some outliers. We had one major one, and then the other one wasn't that obvious. But the thing is, outliers can actually have a powerful effect on your correlation, especially when they are in one of the four corners of your plot. So if you have one like here, you have an outlier here, and then the rest of your, scatter plot is kind of like this. I mean, this whole mess right here doesn't even look like it's much of a correlation. But given the fact that you have these outliers over here, you would literally draw it like that and say it's a positive weak correlation just because of that. So outliers can actually have huge impact on your correlations, and that's why it's good to go ahead and start out with your scatter plot when you have data, so you can kind of see what your, identify your outliers and kind of figure out what your data is doing. Okay, because the thing is, outliers can even change your correlation, going from like strong to weak or moderate to weak, or it can change, it can switch around your correlation. Okay, so it can kind of tell you a different story just because of those outliers, and that may or may not screw with your study or your data, what you're doing. All right, now let's get into something a little bit deeper. Okay, so we're gonna look at correlation coefficient. Okay, remember coefficients from CV, from coefficient of variation a couple weeks ago? So coefficient just means a number, right? So what we're going to be looking at is the sample correlation coefficient. We're not going to be looking at population correlation coefficient because like I said so many times, most of the time out there in the world, when you ever need to use this, if you're going to be using this, in your work or in your grad school, if you're doing research, most of the time you're probably going to be taking samples, not necessarily looking at the population or gathering information for census. You might, but more than likely the most common thing to do is working with samples, so we're always going to be working with samples. Okay, so anyway, coefficient is just a number. R, okay, R right here, that stands for sample correlation coefficient. So that's what we're going to be looking at. That is the that is the, symbol that you need that is going to correspond to correlation coefficient, okay, for the samples. How you can remember that would be like saying correlation, okay, and just say it with a bunch of R's, and you'll know that the way that we like to symbolize that is just with an R. And just so you guys know that the population correlation coefficient is going to be this Greek letter fancy P thing right here. Although we are not going to necessarily use that, we'll focus mostly on R because, like I said, it's way more common. Okay, so R is a numerical quantification of how correlated a set of X and Y pairs are. Okay, so all you're going to do when you want to calculate R is you're just going to plug in one set, a set of your XY pairs into an equation, which we'll show you later. So this has a defining formula and a computational formula. All right, we're going to look at the computational formula. So whenever we figure out what our R is, how do we even interpret it? What are we even doing about it? Okay, so the R calculation is going to produce a number. You're going to get R. You're going to get some sort of number out of it. Okay, what does that number mean? Well, the lowest possible number that it can ever be, if you do your calculations correctly, would be negative 1.0. Okay, so if it's a negative 1.0, then you have a perfect negative correlation. Okay, all right. And then if the highest possible number that you can possibly get for R would be 1.0. Okay, so if you have a 1.0, then you have a perfect positive correlation. Okay, so more than likely, it's not going to be a perfect correlation ever. So you're probably not going to get -1 or 1. You're probably always going to get like, you know, somewhere in between. But you know what? Even if you were to get like 0.95, you know, 0.95 for R, that's actually really close to being perfect. Okay, so that would be like almost a perfect positive correlation because it's very, very close to being 1.0. Same thing over here. Like if you were to get like negative, you know, 0.9 or negative 0.95 or anything like that, that's actually very, very close to being a perfect negative correlation. That being said, you know, in a lot of these, you won't always get a perfect correlation unless that is what your data is doing. Okay, more than likely in real life, a lot of data doesn't happen all nice and clean and pretty like that and just gives you like perfect correlations. That's usually not the case. So many times you might get R to equal like 0.5, negative 0.48, you know, negative 0.8, or even like 0.75, sorry, you know, could be like that. And then, you know, this will kind of tell you, in a way, it sort of also tells you like the strength and the direction of your data. Okay, so like if it were 0.5, that obviously means it's going in a positive direction, but it's kind of far away from being 1, so that would either be moderate or weak, you know. If it's 0.98, that's extreme, or negative 0.98, that is extremely close to being a positive, or I mean, a perfect negative correlation. It's definitely a negative correlation because we have the negative right there. But since it's so close to being negative 1.0, this is a very, very strong negative correlation. Okay, it's almost perfect. And you know, this would also be a pretty strong, I would say, negative correlation, negative 0.8. 0.75 would probably be pretty, I would say it's either close to being strong or it's kind of moderate. But it's definitely positive because this is a positive number. Okay. Now, what if you calculated R and you got 2.5? You obviously did it wrong, okay? How you know it's wrong is because this is the highest that it can possibly be. The highest it can ever be is 1.0. The lowest it can ever be is negative 1.0. So if you have anything higher or lower than those numbers, then you definitely did it wrong and you need to try to figure it out. Okay, so let's go ahead and look at some examples, some real life examples taken from other studies. Okay, and we'll look at what R is doing in these. Okay, so look at D. Okay, as you can see, the scatters, the dots are kind of, I mean, they're not necessarily close to the line, like close, but they're decently close. And of course, they're going in a negative direction. And I chose to look at negative examples because I feel negative right now because my eyeball hurts. But anyway, that's besides the point. Let's look at these negative examples. All right, so in this one, they calculated R to be negative 0.7. okay? And so this one would probably be considered kind of moderate to strong, okay? Because the dots are somewhat close to the line, but not really. So anyway, that's what this would look like, okay? Now look at E, okay? They calculated R to be negative 0.44, okay? So negative 0.44. Look at the scatters of the dots. They're definitely more further away from the first one, from D. So if you compare them to D, they're definitely further away, but they're still going the same direction, okay? You can tell it's still going to be a negative correlation. It's just the dots are a little bit further away from the line, okay? And since they calculate it to be negative 0.44, we would probably call this one, it would probably still be considered moderate, maybe close to being weak, but not weak yet. Okay, and then you look at F. Okay, so yes, we can see that it's still a negative, direction, right? But how strong is it? They calculated R to be negative 2.5. That's definitely really far away from being -1, right? So it's not very perfect at all. Okay, it's quite weak. And as you can see, these plots are almost all over the place. It's almost like not even a correlation. But it's still a correlation. It's still technically, it's going in a negative direction. So we can definitely see that. It's just very slight. A lot of these, especially these outliers, they're just kind of like really throwing things off for the rest of the plots. And they calculate this R to be negative 0.25, which is definitely going to be considered weak. Okay. Now, looking at some examples of positive R. Okay, so this is another real life example of what it can be. So I guess these people, these scientists decided not to draw their line, but no, we can draw our own line. Okay, so the first one, A, this is definitely going in a positive direction. We would probably draw the line to be about like that, right? And as you can see, the plots, they're somewhat close to the line-ish. I mean, we do have some outliers here and there, but for the most part, they are moving in one direction. We can tell that they are, it's a very obvious positive direction. They calculated R to be 0.66, and it's, a positive 0.66, so obviously we're in a positive direction. This would probably be considered moderate. Okay, they're not necessarily close to the line, but it's still a very obvious direction. Okay, they're not so far out that it's questionable or anything like that, So this is more moderate. The next one, B. This is a very good correlation, or a very strong one. The line would probably be about here, and you can almost connect the dots. I mean, we actually connected a couple when we drew this line. So this one's pretty good. It's pretty strong. They calculated their R to be 0.92. So that's actually very, very close to being a positive correlation, right? That's what a positive, strong, almost perfect correlation, perfect positive correlation would look like. Okay, something like this, where it's almost so close to where you can actually connect some of your dots. Okay. Okay, so now we're going to learn the computational formula to calculate R. And it's this lovely looking equation right here. Okay, now don't let this scare you, because I know it definitely looks quite scary. But I want you guys to think back to when we learned how to do standard deviation and finding the variance or the variation. And in order to do that, we did the sum of squares, right? Okay, so notice that there's a lot of sums, okay, in this equation. So basically, you're going to be fine because it's just going to be like last time. Remember last time when we made some columns, okay, to do this, then we made a couple calculations, and then we added up all the columns to get all your sums, and then we used that to throw back into the equation, and then boom, we were good. Okay, so we're going to be fine, and we're going to work this out together. Anyway, it's a whole lot easier to learn all this stuff and put it into perspective if we have a story, okay? If we have a pretend study to work on. So pretend that we have 7 patients, okay? And they came into our clinic for appointments throughout the year, and we are trying to find something out about their blood pressure. We're trying to see if there's a correlation between their diastolic blood pressure and how many appointments that they need to be seen for over the year. So we're thinking, or we predict, that those patients who have a higher diastolic blood pressure, a higher DBP, will have more appointments, okay? Or they will have required more appointments throughout the year. So what we're going to do is we're going to take the diastolic blood pressure of each patient's last appointment, and that will be our X. Okay, that's going to be our independent variable. Okay, and then we're going to see if the diastolic blood pressure causes Y to happen, which Y is going to be the number of appointments over the year. So we're going to see if a diastolic pressure causes them to have more or less appointments throughout the year. That is what we want to know. Okay. Okay, let's go through the equation and learn how to work it. It's actually really easy as long as you stay careful and you stay organized. That's why we make a chart like this. We're going to make a table first, and then that will tell us exactly what we need to put in each of these, in each portion of this equation. Okay, it will tell us what to put in here, 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 all of that. Okay, and then we'll just kind of, even though it may look a little scary, just make sure that you follow order of operations the whole way. You'll be fine. Totally fine. So anyway, set up your table. Okay, so in this study, we have 7 patients, right? So we're going to go ahead and put our patients right here. This is actually N. Okay, I want to make that clear. All right. So this is going to be N in this equation. All right. Well, that's not true. Okay. The total number of your patients will be N. Okay. So that's what it is, not each one of these. But anyway, okay, so then we're going to go ahead and put in your X and your Y's. Okay, pretend this happens after we already conducted the study, we gathered our data. Okay, so remember X is the diastolic blood pressure. So we have all the different blood pressure readings of the patients, of each patient right here in your X column. And then your Y column was how many number of visits that they had, or number of appointments that each patient had. Okay, so the easiest thing to do right here is go ahead and add all these up, okay, and then add all these up. So our sum of the X's is going to be 678, and the sum of the Y's is going to be 166. All right, so already you have some of these portions of this equation. So your sum of X's, this 678, you're going to put that right here. Okay, that's where that's going to go. And you're also going to put that right here. Okay, and one thing I want to point, well, I'll show you in a minute. Okay, and then your X of Y's, your 166, you're going to put that right here, or your sum of y's. Okay, and then also your sum of y's are going to go right here. Okay. Okay, what you do need to know is that this sum of x's, it's not the same thing as this. Okay, this is not sum of x times y. Okay, this is sum of x, y. Okay, so after we figure out what's going to go in this column, okay, after we figure out the sum of that, that is what's going to go here. Okay, so this is not the same thing. Okay, so do not do that. Also, another thing, right here, this and this, the sum of x in parentheses squared is not the same thing either. Okay, this one is totally different and it's going to come from here. This one, as I showed you in the previous slide, comes from here, and you're going to put that in parentheses, and then whenever you work this equation, that whatever's in the parentheses, your 678 is going to be squared. Okay. So again, this and this is the same thing. This, you're going to put whatever you put here right here. Okay, but it's not the same thing as this. Okay, these two are going to be different. And the difference is that you have to make sure the difference is that this is within the parentheses. Okay, so whatever's in the parentheses, you're going to have to make sure you follow the order of operations. Whenever you put this in this section, make sure you keep the parentheses there. Okay, and when you start to work the equation, then you're going to square this. Okay, it's not going to be the other way around. We're not going to take it from x squared up here. Okay, those are two separate things. Okay, so like I said, this goes here and here, and of course be mindful of that this, when you put it here, you need to keep the parentheses around it, and you're going to square when you start working the equation, and same thing for this section as well. Okay, now that we're done with that part, let's start working through the rest of the table. Okay, so for the next column, for this one right here, how that's going to work is, all this is squaring x. Okay, so you take your x's, and for each one, you're going to square it and put it here in this column. So basically, 70 times 70, or 70 squared, is going to equal 4,900 right here. And 115 squared is going to equal 13,225, and so on and so forth. So you're going to go ahead and go down the entire thing. 105 squared is going to equal 11,025. 82 squared is going to equal 6,724. 93 squared is going to equal 8,649. 125 squared is going to equal 15,725. And then 88 squared is going to equal 7,744. Okay, so that is where we get all those. And then once you're finished calculating all of your x squareds, you add everything up. Okay, you find the sum of your x squares, which is going to be 67,892. Then you take this number and you go ahead and put it where you have sum of x squared, okay, which is right here. Then we're going to go ahead and you're going to go ahead and do the same thing with the y's. So you're going to take your y's and then you square it and you put it here. Okay, so we're going to go 3 squared, which is 9. Okay, 45 squared, which is 2025. 21 squared, which is 441. 7 squared, which is 49. 16 squared, which is 256. 62 squared, which is 3,844. And then 12 squared, which is 144. Okay, so then what's going to happen is you're going to do the same thing here. At the end, you're going to go ahead and take all these numbers right here and add them up. And that is how you're going to get your sum of your y squares, which is 6,768. And then you're going to go ahead and put this number right here. Okay, that's where this one goes. Okay, then what you're going to do is you're going to go ahead and find your xy's. Okay, so your xy's, now we're going to look at this section. What is this? This is x times y. That's what that means. Okay, so all we're going to do here is we're going to take our x, take each one here, and we're going to times it by the y right here to get this. So basically that is 70 times 3, and then we're going to get 210. 115 times 45, we're going to get 5,175. 105 times 21 will give us 2,205. 82 times 7 will give us 574. 93 times 16 will give us 1,488. 125 times 62 will give us 7,750. 88 times 12 will give us 1,056. And then same thing at the very end, what you're going to do is you're going to add all these up, and that will give you your sum of x, y. And then you're going to take your sum of x, y, and you're going to place it in this spot right here. Okay, so I think at this point we actually have all the ingredients to solve for r. Okay, let's go ahead. All right, so remember 7 was our n, okay, because we have 7 patients, 7 readings, so that's going to go right there. Then we have our, sum of xy's, which go here. We have our sum of x's, which is going to go here and here, and remember this one is in parentheses and it will be squared when you start working out the problem. We have our sum of y's, which will go here and here. Make sure it stays in the parentheses and that you will square it when you work out the problem. Then we have our sum of x squares, okay, these guys, which will go here, okay. And then we have our sum of y's, this one, which will go here, okay. And of course this is another n, which is 7. Now you have all your ingredients and you can actually start solving. Okay, so the top part is quite easy. You're going to, multiply this side, then you're going to multiply this side, and whatever you get for here, you're going to subtract this from it. Okay, and that's the top. The top is pretty easy. But when you get to the bottom, it can get tricky, and what you really, really have to be mindful of is using your order of operations. Okay, order of operations, always. All right. So the bottom section, basically it looks like this. You got this section, and you're gonna multiply it by that section. Okay, that's how the bottom looks. That's how your denominator is going to work out. So you got to solve this side, then you got to solve this side, and then you're going to multiply them, and then that's what you're going to get. Okay, and then you're going to get your denominator, and then you work through it that way. Okay. So sometimes it's good to go ahead and separate the two. Okay, so anyway, like I said, your top half is probably a whole lot easier to solve. So you would just have those two sections that you would solve, and then you subtract them. And then boom, so what we would get is 16,658 on your numerator. And then the bottom, well, first you would go ahead and solve this section. So remember order of operations. This section is going to be, you got to square this, okay? And then you got to go ahead and you're going to multiply this, okay? And then we go ahead and subtract the two and take the square root of the whole thing. So again, what you're going to do is you go, you take the square root of this, you multiply these, you subtract this one from this one, and then you take the square root of it, okay, and that will give you 124.74. Same thing with this side is what you're going to do is you square this, okay, then you're going to multiply 7 times 6,768 right here, okay, and then you go ahead and subtract the two, okay, and then whatever you get, you take the square root of the whole thing, and that will give you 140.78. Okay, I know it's crazy. So then what you're going to do is you have these two numbers, right? You multiply these two together. Okay, that's it. Is you're going to multiply both sides, and that is going to give you 17,561.3. Okay, so then, haha, you're at the very end. Yes, finally. Okay, so you already calculated your numerator, remember? And then you got your denominator finally. So we got that. Now all you got to do is divide 16,658 by 17,561.3. And then that will give you 0.949. And as we learned already, if it's positive, we're definitely going to have a positive correlation or a positive, it's going to be a positive direction, okay? Our correlation is going to have a positive direction. And given the fact that it's close to 1, right? It's close to 1.0, that means it's going to be pretty strong. This is actually really close to having a perfect correlation, a perfect positive correlation. So, all right, so let's learn a couple fun facts about R, because I think there are a couple things that I didn't necessarily mention, and they may actually be kind of important for you guys to know about R. Okay, so first of all, R requires data with a bivariate normal distribution. And we didn't really go over this in class because I feel like this is a bit complicated, and this is sort of, an intro to stats. So just know this for future statistics classes. If you are going to take, more complicated, higher level statistics classes in the future, R will require data with a bivariate normal distribution. Okay. Anyway, R also has no units. Okay, so we're not looking at any kind of units. It's more of a constant, or it's a number. Okay, it's a number that it's a number that tells us what the data is doing. If I were to just let you guys just simply, it's just a number that tells us what the data is doing, okay? What direction it's going, what's happening with our data, okay? Also, a perfect linear correlation, like we already saw earlier in this lesson, would be when R is either a negative 1.0 or a positive 1.0. Okay, so depending on the direction, if it's a negative 1.0, it would be going in a downward direction, and if it's a positive, 1.0, it would be going in an upward direction. Okay, but also if there is no correlation at all, then R would be 0. Okay, and so just like how we can kind of figure out like if there's a strong or weak negative or positive correlation, we can also kind of do that with when there's no correlation as well, because it's not when there's no correlation, R isn't always going to be 100% 0. R, when you calculate R, you try to figure out what your R is, you could actually get something that says like 0.00003 or something. And if you had that, I would not say, you really should not think that that is just a weak positive correlation. I would say that is definitely going to be a no linear correlation. Okay, even though it's not 100% 0, it's very close to being 0. Okay, so if it's pretty much if it's close to just being 0, if you have a couple zeros in there before you have any actual numbers in your R, then yeah, let's call that no correlation. Okay. Also, positive R means as X goes up, Y goes up, and then as X goes down, Y goes down. Remember? So remember our positive R is like this, and as X increases, of course our Y increases, and then over here when X is low, our Y is low. So Y follows X, like exactly. But when there's a negative R, okay, it's like this, right? And this basically means as X goes up, okay, as X, up here goes up, Y goes down, see? And then as X goes down, where X is lower, Y is higher. So it has the opposite effect, okay? Then also, you guys need to know that even if you were to switch X and Y on the axes, you would still get the same R. R would be the same regardless. So if you kind of made a mistake and, switched your X's and Y's, you got a little confused, you would still get the same R, so you would still know the direction of your data, okay? Even though you definitely want to not do that because it could screw up other things, but you would still have the same R. Okay, and also even if you converted X and Y to different units, like for some, if you were in America and you had like inches or something, those were your units that you were working with, and then you went to the UK and you were like, oh, I need to convert my study into like the metric system, you can do that and you would still get the exact same R. Okay. So another thing that we need to look at, or that I need to, make sure of, is that we know that correlation does not mean exact, like causation. It does not always mean causation, okay? So yeah, we're trying to figure that out, like whenever we have we're trying to figure out if X causes Y to happen, and that's pretty much the idea behind this. We're trying to see if it could be causing a reaction, but we have to be really careful with our words because it's not always that clear that that's exactly what's happening. So in science, we can't necessarily say that this is that X is definitely causing Y to happen. There could just be a correlation. So that's why we use the terms correlation. Okay, so it seems like they're related in some way. Maybe we need further research to figure out if X is really causing Y. Okay, so yeah, X and Y, it can be really political, and we have to be careful to not say that X necessarily causes Y to happen. And I'll show you kind of, I think, oh yeah, here's an example right here. So for example, if we had, if we said that tall people are heavier, no, that tall people tend to be heavy, and X equals height, so the tall people are down here, short people are here, and then we said that Y is going to be weight. Well, sometimes short people can also be really heavy, okay? Some tall people can be light. Some tall people might be very, very skinny. Some short people might, be quite large. So, we wouldn't, it doesn't necessarily always mean that tall people are heavier, okay? Also, so there are other causes of, being heavier than just being tall, okay? While a lot of tall people might be heavier, that's not the only way you can get heaviness. So we have to be careful about lurking variables. Remember what lurking variables are? They're those variables that kind of link certain variables and cause a correlation between them, but it doesn't necessarily mean that one thing is causing the other to happen. Okay, there's there's a lurking variable in there that is kind of tying the two together, but they're really actually not related. Okay, so an example of this could be eating ice cream causes murders to happen. Okay, because when more ice cream is sold, when ice cream sales go up, murder rates rise. Wow, that's crazy, right? Well, what's really happening is when more ice cream is sold, it's usually during the summertime, right? So there's a lot of warm weather, people are outside, they're running around, they're more active, they're getting all hyper, and they're doing things, they're going places, and they're eating a lot of ice cream, okay? So summer definitely increases ice cream consumption, and it also means since people are outside, they're doing more things, and they're exposed to a lot more people, and murders more murders occur. So in this case, summer and warm weather would be lurking variables. Okay, these are two variables that are linking ice cream sales with murder. Okay, because I don't know about you, but when I eat ice cream, I don't necessarily get mad enough to murder. Okay. And also, when the weather is really cold, the murder rates usually go down. They are reduced. And why is that? Well, people are not outside, they're not exposed, they're not frisky, they're not doing things, so murders will decrease in the wintertime, usually when it's really cold outside. So another lurking variable example that we should, just to give you an idea of things you need to be careful with. Okay, so here's another claim that over time, as people purchase more onions, the stock market rises. Okay, this is true for many generations in the United States. Well, what really is happening is that when the economy is going well, the economy is booming, there's a lot more money circulating in our, in our system, then people have more money to buy healthier food, right? Or to buy more food. including onions. So onion sales would definitely rise, okay? And that would, you know, boost the stock market, okay? People are healthier, they're spending their money, they're doing more things, you know, because they have more money. So in this case, a healthy economy, okay, would be the lurking variable. Okay, the economy is what's doing really well, and that's what's causing, you know, more food sales, and it's also causing the stock market to boost, right? So the stock market rises. Okay, so the healthy economy would be the lurking variable that's linking onion sales to the stock market rise. Okay.